Hello, everyone. Welcome to this second series of Kogence webinars. Intention of these webinars is to help you get started, get oriented, and know what about a little bit more about the Kogence simulation challenges. My name is Mokul, and please feel free to interrupt me anywhere if you have a question. This is supposed to be a live session. It's supposed to be interactive. So if you want to stop me, raise your hand, uh, anything like that, feel free to do it. Um, Let me just quickly show you. Let me figure this out. First of all, let me see what share screen. Let me share my screen. Uh, so hopefully everybody is seeing my screen here. This is the Cogence front web page. Hold on 1 minute, just 1 minute. Let me check, make sure that everybody is seeing my screen. Okay, guys. So looks like everybody is seeing the screen properly. So I will get started. And feel free to stop me if you have a question. So today's we're going to talk about our nanophotonics challenge. Um, and let me, before we start talking about the photonics, let me just introduce you how these things will go. So the challenge will be staged in three levels. There would be level one, level two, level three. People who qualify level one, they go to level two, and the people who qualify level two, they go to level three. Level one problem is going to be uh, because there are a lot of participants participating in the challenge. So level one will filter out people, make sure that you are interested in photonics, you have basic idea of how to interpret variables in photonic or optical fields, electromagnetic fields. So the first level is going to be not so difficult. It's going to be easy. It's going to be a uh, uh, it's designed to be able to take out people who are actually are interested in optical engineering and nanophotonics and understand that subject well. Level two, level three are both sponsored problems, and people who qualify level two, they will get some prizes, and people who win level three, they will be awarded final prize in the award ceremony in February 16, 17. Right, so the level one will be open. Problem statement will come out on December 15th and will stay open for a month until January 15th. And January 15th, we will announce who qualified the level one and who is going to the level two. And level two and level three will be open for 2 weeks. For each of the levels, we will give you some free computing resources on our platform. So you can come and solve the problems on our platform. You don't pay for any supercomputing resources. You can use any resource you want. For level one, I would alert you that so you will get 200 CPU hours. The way CPU hours, so you can go here and take a look how the CPU hours work. So if you go on the pricing page here, uh, this is how the CPU credits work. It describes you here. So if you use a one CPU machine for 1 hour, that counts as one CPU hour. So we will give you 200 CPU hours for free to for the level one problem. So don't go and so our platform is a supercomputing platform. So you have a lot of GPUs. You have 128 core machines, and you can use you can make a cluster by combining a lot of these machines together. So you can actually fire 1,000 CPUs in one time, right? But you will burn all your credits right away. So level one, as I said, level one problem is going to be a not so difficult. It's going to be an easy problem. It's going to be a problem around visualization. So we will give you some electromagnetic fields, and we will ask you to plot it, chart it, and visualize it in an aesthetically attractive manner, but without losing the information. So these your charts need to convey as much information in the data as possible to the audience, at the same time being very eye catchy or aesthetically pleasing, right? So it's not going to take a lot of computing power. So I would suggest stay with small machines, one CPU machine or two CPU machine or four CPU machine, and use your time. If you run out of the time, if you, let's say you finished all your 200 CPU credits, you are welcome to purchase more CPU credits from our platform, or you can do it on your local computer. That's fine. You can solve the problem on your local computer and upload the solution on our platform. But we will only consider if your solution is working on our platform. If we try to execute your problem on our platform and it gives an error, then you would be disqualified. So that would not be considered. Okay, so let's get started. Those are some of the basics you want to know about the challenge. Um One more thing I want to point you out is that we are a US based company. We are incorporated in US. We operate under the US laws. So anybody, you need to make sure that you are eligible to receive price from a company based in US. US government does put embargo on a lot of geographical regions, so we might not be able to do any transaction with you. So that's your responsibility before you participate in the challenge. It's your responsibility to make sure that you are eligible to participate in it and receive a prize if you are a winner at the end. Because we won't be able to do any transactions if you're under embargo or any other legal situation like that. Okay, so let's get started. Let me show you. So the first thing you should know about where to find information about the platform. So let me just walk you through quickly. So if you click on the platform here, you can look at the features. So what are the features platform gives you? So it tells you what kind of infrastructure we offer. Uh, our single GPU nodes that are available comes with 40,000 parallel processing cores. So these are GPU cores in single node, and you can then cluster these nodes together to form a supercomputing cluster of your own. Uh, Similarly, if you don't need accelerated computing, CUDA or OpenGL or anything like that, then you can use the CPU nodes. CPU nodes, our single nodes have 128 cores and 4 terabyte of shared DDR memory. And you can again cluster these things together to make a cluster of your own. There is no job queuing in our infrastructure. When you fire a machine, that machine is for you and you immediately get into it. So there is no job scheduling, there is no job queuing. When you submit a job, it's not waiting in any queue. You say that I want a 100 core machine, and you fire your job. We boot the machine for you, and you get that right away. We have a very large model library. We have more than 5,000 models on our platform that are searchable across different verticals, so you can search and get started. We provide all collaboration features. You can collaborate with your colleagues. You can keep the models private, or you can keep them public. You can fork them, or do whatever you like to do with those. Um, uh, Whole platform has enterprise class security, so you should not worry about security at all. If you want to know more about the security, you can click learn more here and learn about security. That's about it. You can read more about you. I don't want to go too much into details because we want to focus on the photonics in this webinar. A few more things you might be interested. If you go on the footer here, there is a lot of information here. So some people had been asking about what are the terms and condition and those kind of things. So terms of use is here. You can click on it, and you can see what are our terms of use. Um, our terms of use, there is a basically a summary on the top, and it's very simple. If you share anything public, then anybody can fork it, modify it. You retain your authorship rights, but you are giving rights to everybody else to copy it and do whatever they want to it, execute it, run it. If you keep your model private, nobody else can use it, not even Kogence. We don't go inside your project repositories. We don't have the permission to do it. We basically cannot do it. So if you keep it private, it's private. We might have to, in very extraordinary situations, we might have to go in your projects. That is generally for security or maintenance reasons, but we will not do that without asking for your permission first. So in any case, even in extraordinary emergency situations, we will ask for your permission first, because we don't actually the platform is designed technologically that we cannot do anything without until you approve it. So that's basically is the summary. You can read more about it. Then the main items for you to get started is the simulators and models. So if you click on the simulators, you will see the different list of different scientific simulators available on our platform. And for the optics or photonics, the ones that are important for you is that you can do some optics using a finite element program called COMSOL. But this is a commercial program, so if you want to use it, you would need to provide the license, or you need to contact us to get the license to use COMSOL. For this hackathon or for a challenge, I would suggest you focus on using open source softwares, free no license software. And the free no license photonic software, we have a lot of them. There's one called FTTD Plus. It's finite difference time domain software that was designed and written in Stanford University by one of my co-founders in the company Kogence. It's a very heavily optimized program. So if you want to do electromagnetic simulation using finite difference time domain, I would suggest you should use this. Then there are other optical engineering programs. There's Lumerical, which is also commercial, so let's not focus on that. Then there is a program called MEEP, and there's another one called MPB, MIT Photonic Band Simulator. Both MEEP and MPB are the open source software built in MIT. These are also very popular software, heavily used, and very optimized. So I would encourage MEEP is again a finite difference time domain software. MPB is an eigenvalue solver. Mesh is a near field optics simulator. And each one of them, right, you can click on each one of them to see what does it do, what are the details here. So for example, I clicked on the mesh. It tells you mesh is a program for computing electromagnetic far field and near field heat transfer for periodic layered structures. Developed in Shan Hui Fan's group at Stanford Electrical Engineering Department, right? And it tells you the details step by step how you are going to use this software. if you want to use it for solving the hackathon problems. And at the bottom it shows you there are a whole bunch of example models on our platform for to make it easy for you to get started. For example, this one is near field heat transfer between two gallium arsenide slabs. uh, so you can click on it and you can see what does it do. There is a little description here, what does it do. There is like what kind of results you're going to look. And if you are interested in modifying this, you can go on the files tab here and you can look at what are the files involved here. uh, so for example, this is the input file. You would have to double click on it to open, so double click on it. And this is a code editor, what this program, how the simulation is set up. uh, if you want to modify this, you would have to make a copy for yourself. So press on this button. You are not allowed to modify somebody else's simulations. That's obvious, right? So if you want to make a copy, if you want to modify this model and use it for your purpose, then you have to first make a copy. Okay. And in the settings tab, you can pick any machine you want. This is not my model, so that's why I'm not allowed to change anything here. But once you make a copy, you will see that you can pick any machine selection, you can pick any software selection, and you will press the run button. Okay, so let me go back to the simulators and let's start focusing on some real world examples on. So those are a few optical engineering related programs, right? So let me introduce you a few more. Rigorous electromagnetic solver. This is a Fourier model method, or basically a frequency domain method. Uh, uh, Method is called rigorous coupled wave analysis or Fourier model method. S4 is another rigorous coupled wave analysis program that came out of Stanford. And Stanford Ray Tracer is a program for tracing the rays. So let's pick one of these. Let's pick REMS and let's dive a little deeper into it and see what you are going to, how are you going to use, right? So this is again, it kind of give you a detail of what is REMS. REMS is a frequency domain wave optic simulator. REMS solves Maxwell equations in frequency domain for both space and time variables. REMS is a heavily multi-threaded, stable, and efficient implementation of rigorous coupled wave analysis, Fourier model method, and S matrix. So REMS is a suite of program that includes S matrix, scattering matrix algorithm. It includes Fourier model method, and it includes rigorous coupled wave analysis, right? And then you have a step-by-step instruction on how to use. And again in the bottom we have like more than 20 different use cases and functional examples using REMS. So lot of cutting edge research simulation models that are very much in focus of research in these days. Near field 3D optical field profiles inside a layer of amorphous silicon nanoholes backed by metal reflector. So these kind of structure people are studying for researching solars. Let me take and there are a whole bunch of examples here, but let me take just a second's break to see if there are any questions or is anybody asking. I don't see any questions here, so maybe we should just get started. Feel free if there is anybody online and want to ask any question, feel free to jump in and ask this question. This is a good time to ask a question. Okay, no? So I'll go back and continue. But if you do have any questions, please do ask any questions. Okay, so let's keep going. So if you look at the more details, so this is kind of just a summary of what does rigorous electromagnetic simulator does. If you want to look at more details of REMS, you click on this link, and this will tell you how are you going to use REMS. REMS stand for rigorous electromagnetic simulator. It's How do you use REMS? What is the usage? So REMS is basically uh, has a MATLAB based API, right? So all you don't need the license of MATLAB. This is an open source free software, so you don't need a MATLAB license. But all the input files that go into REMS are written in MATLAB syntax, right? So we have a MATLAB based API interface to REMS, and REMS is a very user extensible. Users can extend it. User can define a lot of different things in this simulator. You can define new geometries, new structures. You can define what you want to do it. You can define your own charting algorithms, own plotting things. So, and all the functionality of MATLAB can be used. So if you want to plot fields using any of the MATLAB functions, so we have a full-fledged MATLAB API, right? So you can use any MATLAB functions inside REMS, and you don't need a MATLAB license for doing that. So there are three types of scripts a user will write if you are trying to use REMS. There is a script called user-defined scripts, and they should end with a file extension UDS. UDS basically just stands for user-defined script. Then there is a file called problem definition file, and its extension has to be .prb. This is the main file in which you are going to define your problem, like what is your structure, what is the angle of incidence of the light, what's the wavelength of the light, those kind of things. You basically define your problem. What is the what is it that you want to simulate? Then there is a file called command file, and it needs to end with an extension called CMD. The command file defines the flow of the let me step back, right? REMS is a program that people use for doing inverse optical design or optimizing your structure. So let's say you simulate one structure, and then let's say you simulated a grating with a certain periodicity, and then you want to scan the periodicity, you want to change the periodicity and simulate again, right? You are trying to optimize for the periodicity. So when you are doing that, that's what you do in the command file. So in the CMD file, you define what are the variables I'm going to change and run the simulations again. So this is kind of a batch processing. In the CMD, you can run like thousands of experiments on thousands of different optical structures and collect all the information from in one place and then analyze it. We'll walk you through a little bit more on those, right? So those are the three main user-defined files. One is UDS file, one is PRB file, and one is CMD file. Now, the user-defined file UDS files, they themselves can be used for different types of purposes. The three main UDS file you will come across is one is called geometry UDS file. In the geometry UDS file, you define the geometry that you're trying to simulate. And we'll go a little bit more into all these files, right? Normal vector field UDS file is there is an advanced method within the Fourier model method that's called normal vector field method, NVF method. So if you are using normal vector field method, NVF method, then you have to define your normal vector field, and that normal vector field is also defined using a UDS file. And then there are post-processing UDS files, right? So if you're trying to create, let's say you simulated your structure, you calculated your optical field profiles, and you're trying to plot them or chart them in different ways. This is the file you will use a lot in this challenge, I think. So you will use the post-processing file. This file is written in a MATLAB syntax script, and you can use any command in MATLAB. You can do surface plots, you can do 3D plots, you can do contour plots, streamlined plots, cross sections. You can do anything that you can do in MATLAB in this UDS scripts. And again, you don't need the MATLAB license. We have a full MATLAB API, so whatever you write in this, it will execute. Okay. Then there is let's go into a little bit of a detail about the PRB file, right? PRB file is a very important file. This is the file where you are going to define your geometry that you're trying to simulate, or the problem that you're trying to simulate. Here is an example PRB file that we have posted here for you. So some of the variables are kind of a common variable, right? You give a name of your project. Uh, you tell them where is your project directory, and everything will get stored inside the project directory. You define an input directory. There are so input directory contains material files, right? So uh, refractive index of different materials, amorphous silicon, aluminum, silver, gold. So we provide you a lot of input files for a lot of different materials, in both N and K, so complex valued refractive index. But you can define your own. If you want to define your own, you just define a file and put that inside this input directory. Uh, okay. Then there is a geometry definition directory, and we'll go more into this. The geometry definition directory contains geometry UDS file where you define your geometry using MATLAB syntax. And we provide you a lot of common geometries. Like we provide you geometries for example, circular pillars in a square lattice. So lot of nanophotonics type of application, like photonic crystal types of application. So square pillar in hexagonal lattice, circular pillar in hexagonal lattice, holes in a hexagonal lattice or square lattice, pyramids, um, uh, wood pile structure. So we have already provided you a lot of different geometry files, but you can define your own. Okay. uh, and then you are going to define a few so as I said, RAMS is a package of many different types of simulators. So you would say that what simulator do you want to use? So number one, so here you will define the simulator type, and MG stand for the original authors of RCW algorithm, Mohoram-Gaylord. So this is a Mohoram-Gaylord algorithm. This one is a Fourier model method invented by a Chinese scientist. His name is Liefeng Li. So this number two is a Liefeng Li's RCW algorithm. Uh, Number three is Liefeng Li's RCW algorithm with symmetries. So if your structure has a symmetry, you can actually speed up the calculation by a lot. So for example, if you have a C2V symmetry, C2V symmetry meaning you have two mirror planes on which the structure has a mirror symmetry. For example, if you had a square pillars on a square lattice, then that would have two C2V planes with two mirror planes with C2V geometry. If you had that, yeah, then you can speed up your calculation by factor of 8, which is gigantic, right? So in that case, you will choose, if your structure has symmetry, then you will choose simulator type as 3. Then we have normal vector filled algorithm. And then we have a fifth one, which is called MA, stands for my name, actually, Mukul Agarwal. This is the algorithm that I built during my doctoral thesis. And this is algorithm which is very efficient for optimizing random structures. So if you have a randomly textured solar cell on which you want to optimized absorption, then you can use this kind of a algorithm. Okay, so let's keep going. Then you can tell what type of properties you are trying to simulate. So the first one is uh, absorption, reflection, and transmission. So if you only want to simulate far field reflection and transmission and total absorption in the structure, then you should pick the choice one, because that is a very efficient and very fast choice. It will not give you detailed field profiles inside your structure. but it will do the near field simulation. It's not a far field simulation. It will do the detailed nanophotonic simulation and give you reflection, transmission, and absorption. It will not give you detailed field profile, even though it solved the detailed Maxwell equations. Right now, let's say you want to in the kind of structure you simulate in RAMs, they are typically layered structures. Let me see if I have a picture in this. I don't have a picture in this one, but I can show you later. They're typically a multi-layer structure, and each layer itself can be a photonic crystal. So think of it as a multi-layer stack of photonic crystals or multi-layer stack of gratings. That's the kind of structure you are trying to solve in RAMs. And if you say that, okay, I just want to know how much light is getting absorbed in each layer, then you should pick the second one. The third one is that you want to go into a lot of details. You want to say, no, my structure is made of 5 different materials, and I want to know how much light is getting absorbed in each material. Then you will pick the third one. And the fourth one is if you say that, no, I want a fully detailed 3D optical field profiles inside the structure, then you will pick the fourth one. Right. And then for the choice number 3, when you are trying to calculate absorption in each material, so you say my structure is 5 material and I want to calculate absorption inside each material, then we have to do the integration of optical field inside each region, right? And then we offer many different types of integration methodologies. We use Newton Cotes integration algorithm, and you can provide what is the order of Newton Cote integration you want to use. As you increase the order, your your accuracy increases, but speed goes down, right? And then there are some flags here that control whether you want to override your results and stuff like that. This one is very important, I think. When in the beginning, when you're trying to play with your structure and you're trying to solve a problem, you want to switch this flag on. If you switch this flag on, then the program will generate a visualization of your structure, a 3D visualization, and actually show you what you're simulating. But if you're doing a bad, so this is good for first simulation, right? But eventually the main use of this program is to optimize something. When you want to simulate thousands of structures, then you should switch this flag off, because you don't want to visualize thousands of structures and generate 5,000 different windows on your browser. Uh, uh, let me pause here again for 1 minute and see if anybody has any questions. Please let me know if there is any question. So there is a question from Maverick James. He's asking, when will the problem statement be released? The problem statement would be released over this weekend uh, on December 15th. Uh, is there any other question? If you have any other question, please type your question on the chat window. I'll just wait 10 more seconds to see if anybody has a question before we keep going forward with the webinar. Okay, so let me get started. There is one question from Maverick. He's asking if basically how difficult these things are. If you are actually and say an undergraduate student, you are interested in learning, but you don't have a background. Well, that's the main purpose of this hackathon, right? So the reason we started this company is because we want to democratize the access to science. Right now, we think that high-end science is not accessible to a lot of people because you need software licenses, you need powerful machines, you need some examples to get started. There are beautiful open source software built by these large universities like MIT, Harvard, Stanford, there are Wisconsin, but they are not accessible. People don't know about them and they don't know how to install them, how to set them up, where to find the examples, how to get started. Those are the main purpose of this company. We want to bring this scientific ability to everybody. So absolutely, if you are the main purpose of this platform is to encourage undergrads like yourself to get started and explore. So that that's the um main purpose. So definitely, I would encourage you to actually look at lots of examples available here and try to read them and copy them and simulate yourself. Okay, so I'll get going and get started. We'll keep talking about how does these PRB files are structured and what do they do. So so we are looking at the PRB file, which is a user-defined file. It's written in MATLAB syntax. If you are aware of MATLAB syntax, you can see all this syntax is MATLAB. You don't need MATLAB license. This is how you define the structure for REMs. So first parameter here is the structure type, and structure type rect basically means rectangular lattice, rectangular elements in a rectangular lattice. Then you define what is the periodicity in the x-axis. We are talking about periodic structure because we are talking about lattice. Then what is the periodicity along y-axis? So we are saying that my periodicity along y-axis is 500 nanometer. It's telling you what is your cover material. Cover material basically means from where the light is coming. So we are saying that my cover material is air. And what's your substrate material? My substrate material is also air. So cover is from where the light is coming and substrate is where the light is going. Both cover material and substrate material are considered to be semi-infinite. And your main optical structure is sandwiched between cover material and substrate material. Okay. Then we say, what is the groove material? So think of, uh, as I said, right, all the structures that you're trying to simulate in REMs, they are made of photonic crystal in one layer and then many layers stacked on top of each other, right? So, and any photonic crystal layer can be thought of as made of groove materials and ridge materials. So here we are saying so groove is like kind of a hole and ridge is kind of, so this, think of a grating, right? So there's a hill and a groove and a ridge and a groove and a ridge and groove, and they periodically repeat in two-dimensional, not just one-dimensional. So here we are telling my groove material is air, so my holes are made of air, and rest of the material is made of silver. And all these material names that you're writing, there needs to be a material property file in the input directory, as I told you, right? By exact same name. So here, Sopra is if you guys don't know, Sopra is the name of a optical properties database. So this property probably came from Sopra database. That's why it's named as silver underscore Sopra. And if you go into the input directories of this project, you will find a file name by that exact name, silver underscore Sopra, right? Then the other parameters here basically tell you what's the duty cycle of the periodicity. So for example, fill factor zero point 0.5 basically means my duty cycle of the periodicity is 50%. So 50% material is filled with silver and 50% is filled with air. And that's true for both x-axis and y-axis. So it's a two-dimensional photonic crystal with 50% periodicity. And what is the height of that layer? And note that in MATLAB syntax, these are all arrays. So in this example, there is only one number, but you can stack multiple layers on top of each other, and this would just become an array. So you will put, comma, you can put more numbers here. Okay. Then here in the bottom, you're defining your grid. How many grid points in x-axis, how many grid points in y-axis, things like that. It's a frequency domain method. So you have to define how many frequency components you want to include in your simulation. In optical terminology, we call them harmonics. So how many harmonics you want to include in x-axis, how many harmonics you want to include in y-axis. And all these details are available. The link that I showed you before, all these details are available if you want to know what is the detailed meaning of each parameter. Here you are defining the angle of incidence of the light. Psi and psi and delta are the two angles in 3 dimension, right? So you have to define two angles from which the light is coming, right? Uh, we can simulate conical incidence. So this is called conical incidence when the light is coming from a 3-dimensional geometry. That's called a conical incidence. So this RAMS is a very powerful program. It can simulate conical incidence. So you can define two different angles. You can define what are the wavelengths you are trying to simulate, and you can define a whole range here. You can define a whole range of angles of incidence. So the RAMS will go and simulate every wavelength and every angle. So you can study your structure. For example, let's say you're trying to simulate a solar cell, and you say that what is the absorption of the white light at different wavelengths, and as the sun moves along around the sky over the day, how would my solar cell absorption will change over the time, over the day. So you can do all those things here, right? And then the second one here is that, so that's about it, right? That's the PRB file. Then the second important file is the CMD file. And as I told you, CMD file is the file where you define, like, let's say you're trying to do batch processing and you're trying to simulate thousands of the structure and you're trying to optimize them. That's what you do in the CMD file, right? So you find in the CMD file, you will define a sequence of uh, subroutines or smaller components of the program of REMs that will be executed sequentially, right? So here we are first saying that first initialize the simulator, then uh, uh, process my geometry, called geometry processor, then call the refractive index interpolator. So interpolate my refractive index, right? Blah 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 blah. That's how you go through it, right? So let me see if I have it. Yeah. So this was the first file. This is an example file which is very straightforward. We are not really doing any batch processing. We are not actually simulating thousands of structure. We are just simulating single structure here, right? And important one is the last one you should notice, plot and save.uds. So after running the simulation, this is again a MATLAB formatted file. In this file, you plot the parameters that are of interest to you. And we will look into that file into a little bit more detail as well. Uh, and here is another example of the CMD file, right? And in this example, we are saying, how do you go around and simulate thousands of structure? How do you change a parameter and do the parameter sweep? How do you do optimization, right? So again, the CMD file is a MATLAB syntax file, right? So I am calling simulator initializer, and after that, I am making a for loop, right? And I'm changing this thickness variable called T1 and making a two-dimensional loop here. So I'm actually, uh, my guess is that this T1 and T2 are the thickness of the two layers of, so I'm simulating multi-layer grating, and the T1 and T2 are the thickness of two multi-layers grating layers. So we are scanning those variables, and then we are calling, because you're changing the thickness, you have to call the geometry processor again. You have to call the refractive index interpolator again, and then you save your data for each simulation, and then you loop around, right? And then you don't need to call the simulator finisher and plot and save multiple times, because you want to just plot after collecting all the thousands structure data, right? So that's the beauty of the CMD file, that you can decide how you want to loop around. So I want to give you an example, right? Let's say you are not changing the geometry, but you are only changing the wavelength of the light, right? Then you don't need to call the geometry processor again and again. Then your loop can start here. You will only call the geometry processor one, and your for loop will start before this refractive index interpolator, right? So that's the beauty. That's how you optimize your structures. Um, okay, let's keep going. I think so. Now let's look at one of the examples and let's just walk through a little bit more, right? So here is one example which does optical simulation of a square lattice of a nanopyramids of aluminum with square base. Okay, so let's take a look what is in there. This one may be a little too complex example to get started. Let me pick a smaller example. Uh, let's do this one. So there's an optical simulation of scattering from hexagonal lattice of circular nanopillars of aluminum. This one is a simpler geometry. So let's look at this one first. Okay, so it's a hexagonal lattice. Um, those who have, you might say, hey, this is not a hexagonal lattice. You need to have this is kind of a little tricky, right? So this is a smallest cell of a hexagonal lattice. It's called a unit. It's called a primitive unit cell. So if you tile many of these next to each other and up and down, then you can see they will start making an hexagonal lattice, right? So that's the point. And these are circular nanopillars. So there are pillars of aluminum here. There is a quarter pillar here, and there is a quarter pillar here, and a quarter pillar here. So we cut a unit cell. This is a unit cell. But if you tile these things together, you can see that the pillars will make a hexagonal lattice, right? So let's look at what are the files in this simulation, right? So you click on the files here. Let's look at the first file, which is the PRB file, right? So you double click on it. So for opening any file, you should double click. You double click on it. This is the input file. And there's a lot of description and comments on this file, so you can easily understand what is it doing. We kind of looked into the this file structure already in an example, so I'm not going to spend too much time. Important things to note here is that this now the structure type here, it says circ underscore hex, which is meaning circular elements in an hexagonal lattice. And then we are just defining periodicity x, y, what are the different materials. So here it is CSI stands for crystalline silicon. So we are simulating light is coming from a crystalline silicon material, is going into air, and the pillars are made of aluminum, right? And so I will not go into details of this file because we already talked about quite a bit. Let's look at some other files. Let me show you. So this structure is circ hex, circular elements in hexagonal lattice. And where is that geometry defined? That geometry is defined inside this folder. So there is a folder called geometry definition. You double click on it. That's what I was saying, that we provide you a lot of different geometries already, but you can define your own, right? So let's look at how does that circ underscore hex looks like. It's a UDS file, meaning it's a MATLAB formatted user defined script. Double click on it. You can see, and there is a lot of comments on the top, which exactly tells you what this file is doing. And let me just quickly, first of all, in the top, we check that all the input variables are being supplied into the script correctly. So that's not that important. Basically, all this file does is, right, it's again, if you just quickly look at it, it's a MATLAB formatted file, right? And all that file does is that it defines a grid. So here you look at here, right? Let me show you. So Where is it? Here, right? So XP meaning what are the grid points in X direction, YP means what are the grid points in Y direction. So we are defining an XY grid, and then we are assigning materials into each XY point. That's all, right? So let me see here, right? So these are circular elements. So we are defining a variety of circles. Epsilon 2D meaning permittivity in two-dimensional. So when you assign materials to different regions, you are basically defining permittivity, right? So all we are doing here is that we are defining circles and we are assigning different materials to different regions of that grid. So we are saying epsilon 2D is a 2D matrix, and within a circular region of that matrix, I want to define this material and other materials, right? So that's all the you. I don't want to go line by line, but you can read it and understand it. It's very simple. You define a grid, and in that different regions of that grid, you define different materials. That's all, right? So if you have a new type of a geometry, you can write a file like this yourself. Let's go and look at some other files. I think one another file you might want to look at is the plot and save.uds. So double click on it. Again, this is again a MATLAB formatted file, and you can see that we are defining variety of different plots. So we are plotting wavelength versus number of photons being absorbed inside the structure and things like that. Again, you can plot whatever you like. So the level one of the hackathon is going to challenge you with plotting. So this is the file you want to look into in details. And you don't have to use RAMs for plotting. You can use Python, right? You have the data, and I just want you to plot in let your imagination fly and plot it in fancy ways. So I'm going to give you four-dimensional data, five-dimensional data, and you need to plot it in a attractive fashion. And you can use, if you're good at Python, if you're good at Matplotlib or SciPy, NumPy, go ahead, use those. And we have some more programs around plotting, like ParaView, Vista, VMD. You can use any of those. So I don't care, yeah, right? You use any program. So let's just walk you through this. How do you run this program? So you go settings here. You pick which type of machine you want to run. So right now I'm picking 16 core CPU machine. You can pick any machine here. Again, be very, very careful for the level one. So we have up to 128 cores machine. I would tell you be very careful for level one because you will get 200 credits. And if you fire a 128 core machine, you will use 128 credits out of it. So you would be left very few. And the level one problem is very simple. So I will encourage you to pick smaller machines so that you can play around with the problems and do a lot of things, right? These bigger machines would be useful if you qualify out of level one and go to level two. Then problems will get more intricate and would need more computing. And we will give you more free credits as you graduate to level two and level three. Right. And so once you do all that setting, you go to the software here, and that's how you run the RAMs. I'm actually going to delete the MATLAB because you don't need MATLAB. You can add multiple programs here in sequence, right? We don't need MATLAB, so I'm going to delete all these things. And then you save commands, and that's how you run the RAMs. You provide your name of your CMD file and the PRB file, and then you press the run button here, and the simulation is getting fired into the 16 core machine. It will take about 2 minutes for machine to boot up first time. So we have to wait 2 minutes before we click the visual button here. But I want to point it out. This 2 minute wait is only first time you click the run button. After that, let's say you made a mistake in your program, you can stop your program, come back, edit your program, and press the run button again. Then there will be no lag. Okay, so this is going to take me about 2 minutes for this visual button to come up. So let's take a break and see if anybody has any questions. So we can take any questions if you guys have anything. So I see a question which is saying that if there are any reference videos where you can see simulations happening instead of written examples. Yes, there is one. There is one example video right on the front page, and we will be posting a few more video examples. So right here, actually, watch demo here is the. So if there are any other questions, please let me know. I'm here while we are waiting. So let's go back and see if our visualization button became active. Sometimes you have to refresh your window, okay? There might be some bug there. Sometimes this visual button don't come by its own and you have to refresh your browser window. I don't know that's a bug or if it is just the internet connection breaking down. So see, I refreshed my window and this visual button came right away. So sometimes, just be careful. Don't just sit there and wait. If it has been more than 2 minutes and it's not coming up, refresh your window. So let's click on the visual here, visualize. You will be connected to the remote machine that we just fired, the 60 core machine, and you will get a remote desktop basically, right? So you can do whatever you will. It feels just like you're sitting in front of that machine. So here is that machine, right? And this first window that you see here is a resource monitor. So you can click on the resource tab here, and you see we fired a 16 CPU machine, and you see the 16 CPUs here. They're not being used right now because I am guessing that simulation is still initializing. It has not started running anything yet. And these windows will give you any output if there is any error or any warning messages. I am hoping these curves, these graphs will start picking up as the simulation gets initialized and starts running. So let's just cross our fingers and see what happens here. Here you see that the simulation has started, and for it was a very small simulation actually. It's already finished here, by the way, and you can see that when the simulation was actually crunching a bunch of data, then it hit the 100% CPU usage, right? And these are your field profiles. You can expand it, and these are the field profiles that got simulated in the hexagonal lattice, right? So you can do, you can save it as a JPEG or anything if you want to. And one thing I want to tell you, right, like if you save it as a PNG or a JPEG file, all your data gets saved. Let's try it, right? Let's try it. Let's give it a new name and see. So let's say file, save as. You should typically save anything inside figures directory, I would say. Right? So you go inside figures, data figure test. I'm gonna call it test one, and I'm gonna save it as say JPEG or something, right? Uh, let's just use this file browser. I want to show you your job folder, right? So whenever you fire a job, you get a job folder which is /temp/user6, and this is the job number. All your files will be stored in this folder. So, and you will see everything here. So any file you save it back, you should save it back into this folder. If you save it anywhere else, it will not sync back to our web server. So right now you are into a computing machine, right? Remember, this is a remote graphics into a computing machine, the 16 core machine. You're not sitting on our web server. Right now you're looking at the 16 core compute machine. And if you have to save everything inside this folder, if you don't save it inside that folder, that will not sync back to our web server. So we saved it inside the figure folder, right? So let's kill this job. And this is also important. You should make sure that you're stopping your job. Otherwise, your credits will keep getting used, right? So stop your job. After you stop your job, your files will get synced back to the web server. Not this is the syncing is not real time. It only syncs after the job has been finished, right? So then now let's go and look at it. So we saved it in the figures folder. I hope this the one will show here, the test1.jpg. This is the file that we saved just now, right? So this syncs back. It doesn't open. So, the JPEG file, if you double click on it, the JPEG file doesn't open on our browser, but you can download it, right? So if you right click on it, you can download this file on your local computer. Or you can do it. So any JPEG files actually sync back to Wiki. So any simulation project gets a Wiki page. In the Wiki page, you will describe what this project is about and the results and any new file. So this is the new file that I just saved. This is the old file, which is basically the same. Old and the new are same, right? But any new file you save, they will sync back into Wiki in this section called model new results. And then you can press this edit Wiki button on the top, and you can move things around. It's a full-fledged editor, just like Microsoft Word. So you can insert formulas, you can insert code blocks, you can insert media, and you can move these files around, right? And this is very important for you for the hackathon. Your final submission for us is this wiki page. So you need to describe your approach very, very clearly here. You need to have nice graphics and pictures. And this is what you're going to submit to us to analyze what you have done for the problem in the hackathon, right? So this is your end goal. So make yourself very familiar as to how you're going to edit these wikis and describe what you did, what approach you took, and what results you generated. Okay, so that's it. Let me know if you have any other questions here. So I'm gonna again take a pause for 20-30 minutes. Sorry, 20-30 seconds, and see if there are any questions. So there is a question from Parth Sharia. He's asking what type of data can we expect in level 1? So the problem is not disclosed yet. The problem statement will come out in December 15th, but most likely the problem will come out. So we are still working with our sponsors who are going to sponsor the problem. Most likely the problem is going to be, for example, the electromagnetic fields is a 5-dimensional data, right? So your structure is a 3-dimensional structure, and every point in the structure you have an electromagnetic field defined. An electromagnetic field is a 3-dimensional vector field, right? So it's actually a 7-dimensional data. At every grid point, sorry, 6-dimensional data. Every grid point you have 3-dimensional vector defined, right? So it's a vector field on a 3D volume. So it's a 6-dimensional data. How do you plot it, or how do you chart it, so that it does convey the technical information it looks pretty, and yeah, with one chart you can tell people what's the information in this data. So that's the kind of data you can expect. Any other question? I'm gonna wait 20-30 seconds more. Otherwise, if there are no questions, we gonna close this webinar. So let me know if there are any questions. So Parth Sharia is asking a question if there is any example or practice data available that can be used to see what kind of data you will need to be charting. Uh, all these REMS example that we showed, there are a lot of REMS example on our website. If you go on the files tab and then you go inside the data folder, all these problems have three-dimensional field data. Any other questions, guys? Okay, if not, then let's wrap up. Uh, I look forward to seeing a lot of contribution from you guys over the weeks coming, and watch out for the problem statement coming out over the weekend. Thank you, guys. Thank you for listening and attending. Have a good day.